Hello. Today we'll ground two ideas that turn IoT devices from passive gadgets into truly smart systems: feedback and feed-forward control. In one sentence, feedback corrects after an error appears. Feed-forward acts before the error shows up. The real engineering win is knowing when to use each and how to combine them so your IoT system stays fast, stable, and reliable at scale. A control system regulates a plant or process. It has three core parts: a sensor that measures the output, a controller that decides what to do, and an actuator that drives the input. In IT, devices compare the current state to a set point and adjust automatically, continuously, consistently, and without a human in the loop. Networking just multiplies the impact, many nodes sensing, deciding, and acting in concert. Feedback watches the output and corrects any deviation from the set point. The workhorse is the PID controller P proportional, reacts to the current error, more push. I integral accumulates error over time to remove steady state offset. D derivative responds to the rate of change, damping overshoot and oscillations. Tuning is a trade-off. Higher KP is faster but can overshoot. Key kills residual error but risks integral windup. KD smooths motion but is sensitive to sensor noise. Use filtering and reasonable sampling. In digital systems, we implement PID in discrete time with sums and finite differences. Feed-forward is open loop and proactive. You measure the disturbance and, using a model of the process, compute an input that cancels its effect before it hits the output. When the model is accurate and the disturbance is measurable, response is very fast and smooth. The limitations are clear. Model mismatch degrades performance, unmeasured disturbances slip through, and feed-forward alone doesn't guarantee stability. Think of feedback as your safety net. It handles unknowns and drifts, but reacts after the fact and can be slower if poorly tuned. Feed-forward is your turbo. It delivers quick, elegant moves when you can measure and predict the disturbance, but it relies on modeling accuracy. Neither is universally better. The right choice depends on disturbance measurability, model quality, speed requirements, and robustness needs. The strongest designs combine both. Feed-forward knocks down the predictable part of the disturbance so the feedback loop can run gentler gains, focus on residual errors, and ensure stability. In practice, that means identify key disturbances, build a lightweight process model, add filtering to noisy signals, rate limit actuator commands, and keep anti-windup in the feedback loop. The result is faster response and solid robustness. To wrap up, feedback corrects, feed-forward anticipates. Together they deliver responsive and stable IoT control. As you design, start by defining the set point and sensing chain, tune a reliable feedback baseline, then layer in feed-forward where you can measure and predict disturbances. Keep models simple, filter wisely, and validate with step tests and safety limits. Thanks for watching. Check your understanding with a short quiz in Classroom, and I'll see you in the next session.